Yeah. It's a very good afternoon to all of you. Am I visible and everyone over here? Yes, Priyanka is there. Okay, Nayak. In a particular group, though, it is already fixed, no beta. According to periodic table only. What is your specific question? You should be like more clear about it. I'm not able to get your question appropriately. Maybe you can reframe it. Okay, I hope. How was your test, by the way? How did you people write your test? Yes, Trishal, a very good afternoon. Jyotika, good afternoon. How was the test, beta? Everybody has written nicely? Yeah, good. If I think it was easy only, provided if at all you have studied, you will find it easy, right? So everything needs some kind of practice, and those were all already basic questions, right? I hope you people are comfortable with that, and I hope everybody is revising the things which are being taught from here. Okay, so basically let us start off with the today's session without any further delay. I hope that's absolutely all right for everyone. Can we start off, right? Yeah. So let's begin the session. Okay, fine. So in the last class, I think I have given you this particular thing about the definition of different types of different terminologies I have given you. That is basically typical elements, transuranic elements we have talked about. Okay, and then you can just write down one note over there, right? For bridge elements. As such, not very important. Basically, these elements were kind of identified from the Mendeleev periodic table, right? But the thing is, we just have to see from the modern periodic table what are those elements as such. So basically, not much could be asked, but the thing is, you never know NTA, right? So it's basically just to have like some things like as fact, you should remember it. Okay. So you can remember, you can write third period elements. Third period elements. What are those third period elements? Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine are also known as bridge elements. So they are also typical elements as well as the bridge elements, right? So this is what is actually the thing is, it is from the Mendeleev's periodic table, and we don't have to do much of kind of analysis from there. Only thing is, remember this as a fact, that will be sufficient. Okay. And I hope everybody is comfortable finding out the atomic number of the elements, right? Identifying the elements. Okay. And if somehow you are forgetting also, you should be, ready with the plan B. Sometimes it may happen that you're not able to remember the magic numbers. Not an issue, right? I think in the examination, there was one question where they've asked you about bismuth, right? But at least you should remember something, that is mandatory to sail through the examination. Okay, so what you're having is New Zealand, this one is nitrogen, phosphorus, arsenic, antimony and bismuth you are having. This is group 15, right? Then you'll be having group 16, oxygen, group 17, fluorine, and I'm not writing all of them, right? And group 18 you are having, that was helium, neon, right? Argon, krypton, right? You are having xenon, right? And you are having radon. Okay. Now in this case, I have asked you about, this is basically radon. Okay. So you already know this, at least minimum information is required. I'm telling you this question, reason being, I think few of the students asked me, ma'am, what if we forget the magic number? But the thing is, if your question is, what if we forget the entire periodic table, then God only save you, right? So at least minimum things we should remember, okay? So you are having here 2, 10, 18, 36, 54 and 86. That much we know, right? Now can we do the reverse engineering here to reach up to bismuth? You already know that your entire modern periodic table, the elements are arranged according to the increasing atomic number, right? So can we just come back few steps? So 86, 85, 84, 83. Did I get the atomic number of this? Even if you forget. Okay, so that way you should be able to assess the things. Okay, but something minimum things you should know, from where the second period elements, what are the second period elements, what are the third period elements. Minimum basic thing is required. I hope that is okay with you, right? So I've told you how to approach the problem, even if in the examination due to some nervousness, if you forget that, how to go about it. Understood, everyone? Acha, there was one more question which people felt like helium. So the thing is, helium, which block it is, or which block does it belong to? So basically you are having the last electron is entering into S subshell. So it will be called as S block, right? Some of you, I think many of you might have written it as P block. Now that is the flaw of modern periodic table. Till now, the scientists have not, they have not yet been able to decide where to place hydrogen. And the similar case with the helium also. Helium as such should be placed along with some S block element. But the problem is, helium property matches with the P, this inert gases. That is the reason this is kept there. So I hope you take care of all these small things which are there. Right? I hope this is clear to everyone. Okay, and you don't repeat the mistake if you have done it. Okay, fine. These were the common kind of questions which came up to me after the test, which students have asked. That is the reason I thought of I should discuss, or else kind of discuss with you as well. Okay. Now let us go for learning the main topics here. Trends in atomic properties. This is the main area from where majority of the questions from the periodic table is asked. Okay, because they can ask you to compare the properties. Okay, that's the very common question which could be asked. Okay, and whatever till now we have studied, that is kind of forming a basis so that you can easily identify, because the elements will be randomly given to you. And you will be knowing about how the particular property is going to vary along a period or else down the group, right? But for that, you should know where is the placement of these elements. So unless and until you don't remember your elements in the periodic table properly, you will not be able to arrange the elements according to whatever is the property asked. That is the reason we have taught you first about the modern periodic table in so much detail, right? So that you be very comfortable with all these things. Okay. Now the very first property which comes up is effective nuclear charge, and it is basically Z effective. We represent by this. Okay. Now let us try to understand this first, right? And there is one more terminology which we'll be trying to understand here, which is shielding or screening effect. Okay, shielding or screening effect, right? So let us try to understand and then we'll write it. Okay. Now suppose consider an atom, right? And there is a nucleus in center, definitely. And you are having just one electron and one shell, which we are talking about, right? At this time, definitely this electron is going to feel some force of attraction. Let that force of attraction be F1. I'm just designating it by F1, okay? A random variable, okay? So at this time, there is nothing which is like coming in between this particular outermost shell electron and the nucleus. So this electron is fully enjoying whatever is the nuclear force of attraction coming to it, okay? Now, imagine a scenario where I've brought one more shell here, right? And suppose I give you 2 electrons in the inner shell, and outer shell, there is 1 electron, right? Now you must understand that nuclear force of attraction will try to reach everywhere, right? And let us say the force of attraction which is trying to reach this particular outermost electron is F2, okay? Now you already know that electrons, they are negatively charged, and we also know that like charges repel each other, okay? So if like charges repel each other, so in that case what will happen? These inner electrons, they are going to repel the outer electrons. So when you repel someone, you try to run away from them, right? That's what happened. And if you don't like someone, you try to, kind of find the places where you can hide from those people. Okay, so here repulsion, you can think of pushing that person away, right? So here also the electrons are pushing the outermost inner electrons, they're pushing the outer electrons away from them. So away from them in the sense what? They are increasing the distance of this valence electrons from the nucleus, right? So if the distance from the nucleus increases, do you think that this particular outermost shell electron is going to basically face the same nuclear force of attraction which it used to feel earlier? Will it have the same? No. The thing is, this time it is going to have lesser nuclear force of attraction in comparison to the first scenario. So I can say that F2 is going to be lesser than F1. Reason being, in case of F2, the second scenario, your inner shell electrons, basically they are, what they are doing? Basically they are repelling the outermost shell electron, or else you can think of, they're kind of protecting this outermost electron from whom? From the nuclear force of attraction, right? So that's why this effect is also known as shielding or screening effect as well. Like the way if at all it is rainy season, okay, we carry the umbrella on our head, okay, so that what that umbrella is doing, that umbrella is basically shielding us from the rain, right? So same thing here also. So the inner electrons, they are basically shielding or protecting or screening this outermost electron from the nuclear force of attraction, right? Are we getting it? So we are going to write about this. So I'll say that the phenomena in which the outermost shell electrons are shielded or screened from nuclear force of attraction, by the inner shell electrons. That phenomena is basically known as shielding or screening effect. So I'm writing here, due to repulsion from inner shell electrons, the nuclear force of attraction, I'm just writing the statements what I've already explained to you, okay? So the nuclear force of attraction decreases, this reduced, this nuclear force of attraction experienced by the valence shell electron decreases, and this reduced force of attraction is only known as effective nuclear charge. So this reduced force of attraction is known as effective nuclear charge, right? So I'm writing the formula here, which is Z effective. I'll write down the formula and then we can write it down. No, don't worry about it. Z effective is equal to Z minus sigma. This is the formula which you have to remember, okay? And as such, directly we have to remember the trend. Now the thing is, this is telling you about the atomic number. Atomic number means, that means you have been provided with the number of protons, right? And sigma is shielding constant, or else it is known as screening constant, or else it is also known as Slater's constant. So you first write this down and then we'll proceed further. Don't worry about it. I'll scroll it up after some time. Please note it down. And once you are done, please do the thumbs up so that I can understand that. Okay, good. I think I would scroll up a little bit so that you can write further. Yes, I hope it is done now. Okay. Yes, I have written atomic number and the number of protons. Now the thing is, you don't have to worry about calculating this shielding constant that comes with some formula and all those stuff. We don't have to remember that. Okay. So what is the kind of, take away from this? You just remember effective nuclear charge is just telling you the nuclear force of attraction. Okay. But this time it is why we are calling the term effective, because earlier there was no intervening electrons in between. Now this time you are having intervening electrons which are present in the inner shell, right? That is the reason we are saying that it is basically Z effective. Ultimately, it is also telling you the nuclear force of attraction only, right? There should not be any confusion about it. Okay. And sigma is basically taking care of the inner electrons. If higher is the number of inner electrons, higher will be what? Interelectronic repulsions, right? So sigma is taking care of those interelectronic repulsions. Okay. Now, next I'm writing here basically shielding power, right? Or which has got the best shielding effect or screening effect. Now here, if n value is same, if n value is same, then what we are writing is this shielding power. Shielding power is given by Ns, Np, Nd and Nf. That means if at all there is like S subshell, so it will have the maximum shielding power. That means it will be able to stop or else, kind of protect the outermost electrons to the maximum extent from the nuclear force of attraction. Okay. But what if n value is not same, right? So if n value is not same, then as n increases, shielding power decreases, right? The thing is, as you keep on moving away, n means what? Principal quantum number, and it tells you about the shell. So as you keep on moving away from the nucleus, what happens is, particularly you are moving away from the nucleus, so you don't feel the force of attraction already coming. So what is the, like, there is no need that it will be able to stop, right? So first of all, when you are moving away, as n increases, so what happens? The force of attraction already becomes very negligible. It is not able to feel that force of attraction. Okay. So for example, if I ask you a question for shielding power, let us say I'm asking you 4s and 4p and 4d. N value is same, right? So in that case, shielding power will be like this. What if I give you something like this, 3s, 7p? N value is not same. In that case, who will be having a better shielding power? Definitely which is closer to the nucleus, right? It will have a better shielding as compared to the one if it is away from the nucleus. Clear about this? So please make a note of it. Yes. Good. Next, we'll see the trends of Z effective in periodic table, and this is the thing which we need to remember. And remembering the trend of Z effective will definitely help us out in basically understanding the other properties as well. Okay. Now, when it comes to in a period, right? In a period, we are moving from left to right. Okay. So left to right, what happens is Z effective is what? Z minus sigma. Yes. Now the thing is, when we are moving in a period, Z is increasing by a factor of 1 because the elements are arranged in the increasing order of their atomic number, right? 1 we are increasing. Now when it comes to sigma, the thing is, every time the electrons are entering into the valence shell, inner shell electrons are getting fixed. They are not changing. So basically this is somehow constant, right? So it doesn't have any role to play, okay? So because of that, what will happen? The Z effective, ultimately that is going to increase. Getting it? Why did I say sigma is not going to change? Or else the thing is, you are having the valence electrons only getting added up. Now inner shell electrons are fixed. If at all I talk about second period, you are having 1s2 fixed. Every time what is happening? 2s2, then 2s1, 2s2, 2s2, 2p1, 2p2 like that. So in the valence shell only electrons are getting added up, right? So the thing is, it won't have that much of value actually. That is the reason we have crossed it here, okay? So ultimately, I'll be able to say that Z effective increases, and if that increases, okay. So left to right, it is increasing. Just to remember that we are learning the trend of it, okay. In a group, we normally move from top to bottom. So top to bottom, what happens is both of these factors increases as such. Z also increases, atomic number increases, right? And you are having this inner electrons also increasing up. So basically when we see the overall effect, it seems like it's almost remains constant. So here we write it as Z effective almost remains constant, right? So write this, then we'll proceed further. Yes, hopefully written. Okay. Now let us move towards the second property, which is atomic radius. Now when we talk about atomic radius, that means suppose if I take an atom, then you are having nucleus here, electron here, right? So this distance, basically the distance of the outermost shell electron from the nucleus, it is basically known as the atomic radius, right? Now the thing is, it is difficult for us to determine exactly the atomic radius because we already know basically electrons, they'll be present in the orbital and they just represent the probability of finding the electron, you know, in three-dimensional space around the nucleus, right? So what we do is, for finding out the atomic radius, we try to take the help of the way in which atoms are found in nature. Accordingly, we calculate the radius. Suppose your atom is found in the form of it is found in the form of a covalently bonded molecule. So we calculate the covalent radius, right? If it is present in the form of a metal, right? So we calculate the metallic radius. Okay. If it is present in the form of ionic compound, we calculate the ionic radius, and so on it goes. Okay. So here we are going to write down the distance of the outermost electron from the nucleus is known as atomic radius, is termed as atomic radius, right? And now we are going to write down there are 4 types of atomic radius. First one being covalent radius. Second one, metallic radius. And we are going to represent it like R covalent here, Rm here. Then we are having basically van der Waals radius. Then we are having basically ionic radius. So in this case, I can represent R plus or R minus. It depends upon whether I am dealing with the cation or anion. So please take your time to write this on and then we'll proceed further. And once you are done, let me know. Yes, let us proceed further. I hope people have written this. Okay. Now, the first one is covalent radius. Now, in case of covalent radius, basically there could be two possibilities. I can have homonuclear diatomic molecule or else I can have heteronuclear diatomic molecule, right? So for both the cases, we'll see. First one is for homonuclear diatomic molecule. And when I talk about this term homonuclear, homo means same, nuclear means same atoms we are talking about, nucleus, same nucleus, right? Homonuclear diatomic molecule, right? So for example, if I take a hypothetical like A2 molecule, so that means it could be like Cl2, H2, anything, right? But I have taken hypothetically in general A2, okay? So the thing is, we are having this A2 present in a form of a covalently bonded molecule. You're able to see this, right? So this is basically the internuclear distance between these two A atoms which are covalently bonded to each other, right? Now the thing is, I can show easily like this. This distance I am showing it as DAA, which is also known as internuclear distance, or else I can also call it as bond length, right? Bond length, AA bond length. Now the thing is, if I take half of this distance, right, this distance which you're able to see, I'm calling this as RA, okay? So half of, if I have to define this, so I'll say that half of, this is like half of the internuclear distance of the two atoms, of the two like atoms, which are basically covalently bonded to each other, right? So I can say this is basically internuclear distance, or else even I can call this as bond length, and I can write DAA upon 2 is basically the radius of this A, right? So I'll write down the definition and you can copy down this, right? And I'll write down here, it is half of the internuclear, it is half of the internuclear distance between the two like atoms, which are covalently bonded to each other. Okay, so finish writing this, then we'll see the case of heteronuclear diatomic molecule. I hope all of you are able to read my handwriting. If there is an issue, kindly feel free to ask me. So I've written it is half of the internuclear distance between the two like atoms which are covalently bonded to each other. Yes, are we done? Please let me know so that I can proceed further. Yeah, fine. Now let us go further for, in this only, for heteronuclear diatomic molecule. So for heteronuclear diatomic molecule, that means suppose I'm talking about AB molecule, hai na? It is consisting of two different atoms, right? In general, for an example, so definitely there will be like variation in the size as well, which you are able to see, A, B, and let us say this is the center here, this is also the center of it, that means the nucleus, and we know that this distance, basically this is going to be the bond length of AB, right? So we can write here DAB is equal to RA plus RB minus 0.09 mod of delta X, right? So basically this is just for the extra information. As such, nobody is going to ask you much. And what about this? This is basically representing the delta En of A and B. Electronegativity difference between A and B. And these two, they have been taken in terms of angstrom, right? So this is only for your information that what if you know two atoms are different. In that case, we have to take care of this or else take help of this particular formula and proceed. Right? So please make a note of it and then we'll proceed further. Yes, are we done writing? Okay, good. Now let us proceed further. Now we are going for metallic radius. When I talk about metallic radius, so we already have some idea from solid state that different metals will have different crystal lattices, okay? Some of them may be having HCP, some of them may be having CCP or FCC or else BCC or simple cubic, right? So there are different arrangements and there are basically different types of closed packed lattice which exist for a particular metal, okay? So what we see here is, suppose if I draw arrangement of metal atoms in one of the closed packed lattice. Okay, let us see like that. I'm drawing it. Okay, one of the closed packed lattice. Okay, now the thing is, these all are representing the metal atoms. Okay, I'm not writing in all of them. I've just kind of left two of them. Okay. Now the thing is, what this yellow dot which I've placed, that is basically telling you the position of nucleus in these two metallic atoms which are present adjacent to each other. Okay, so what I'm going to do is, basically you are having this, right? So this is basically the bond length, the mm you can think of, right? So what about the radius? The half of this distance, right? So I'll just, kind of join this. So the half of this distance which we are talking about, this is going to be the radius of this metal, okay, metal atom. So radius of this metallic atom is going to be d mm upon 2. So can I say, if at all somebody asks me about the definition, so I can easily say it is half of the internuclear distance between the two adjacent atoms which are placed in closed packed lattice of a metal, right? That's what is metallic radius. So I'll write down the definition here. It is half of the internuclear distance of the two adjacent atoms present in closed packed lattice of a metal. Closed packed lattice of a metal. That's what is metallic radius. And once you have written, please do the thumbs up so that I can understand. Okay, fine, you are done. Okay, good. Okay. Now next is van der Waals radius. Now when we talk about van der Waals radius, first of all, this is valid for gases, or else noble gases. Gases in the sense, I can have Cl2 gas, H2 gas, O2 gas, N2 gas. For that, van der Waals radius. Now first I'll draw this diagram. Let us say I'm having a sample of Cl2 molecule or Cl2 sample, right? So let us say I'm having one molecule of Cl2 like this, right? Another molecule of Cl2 like this. Okay, this is Cl, this is also Cl, Cl, right? Now the thing is, what I have to, if at all I have to go for van der Waals radius, see the thing is, if at all this is this distance, if I talk about this distance, so this is basically the bond length of it, and half of this distance we know it is going to be covalent radius. But I don't want covalent radius, we've already studied about it, right? Now the thing is, this time we are going to focus on, or else let me choose another color. This time we are going to focus on these two atoms. You're able to see? Are these atoms in the bonded state? No, they are not in the bonded state. This distance is the internuclear distance of them, which is present between these two non-bonded atoms, right? So half of this distance is basically the van der Waals radius, right? And this is basically internuclear distance between two non-bonded atoms. That's what is your van der Waals radius. So I'll say that basically what is this particular van der Waals radius? It is half of the internuclear distance between the two atoms which are present, between the two adjacent atoms which are not bonded to each other. Now you try to understand this basic concept. Basically, when I'm talking about Cl2 molecule, that means I don't have just one Cl2 molecule, right? I'll be having more than that. And gases, they'll be randomly moving here and there, right? Some of the gaseous molecules may be in very close proximity of each other, and some of them very far away, right? So basically, we are considering the closest of the gaseous molecules which can be with respect to each other, right? So that's how we define it, okay? So I'll write down here, definition wise, it is half of the internuclear distance between the two atoms which are not bonded to each other, which are not bonded to each other. So please make a note of it and then we'll proceed further. Good. I hope there is no confusion here, right? You are clear about the covalent as well as the van der Waals radius. Yes, done? Okay, now let us go for the next one, which is ionic radius. Now the thing is, here I am not going to say that it is half of the internuclear distance between the cation and anion, because the thing is, different ionic compound, they are having different types of lattices, and accordingly things will be decided. Because the thing is, if at all you consider NaCl, you are having basically their FCC lattice and the Na plus in the octahedral void. If you take any other compound, so definitely the lattice is going to change, right? So basically we are going to define it in general. What is the radius of, if at all I want to say for a cation, and what is the radius if at all I want to define for a particular anion. Okay, so in this case, ionic radius, which I am talking about, so basically I can have just like this as electron. Now this radius could be r plus if at all I am thinking of a cation, and r minus if this I am considering it to be anion, right? So the thing is, this could be representing a plus ion or else x minus ion. So if it is x minus, this is anion. If it is a plus, this is cation, right? So the thing is, if at all I am considering this species to be cation, so basically I'll say that it is the distance of the outermost electron from the nucleus, right? That's what is ionic radius here, right? So it is the distance of outermost electron from the nucleus of a given ion. That's what is ionic radius. Now there is one order which I am going to write down, that is van der Waals radius biggest, then comes your metallic radius, and then comes your covalent radius, right? And this is important, do remember that, right? Already you know, in case of van der Waals, already things are the internuclear distance which we are talking about, it will be anyhow very large. What about metallic? If at all you consider metallic radius, suppose only two metal atoms. So basically this internuclear distance is going to be more. In case of covalent, are you able to see that because of this overlapping, this internuclear distance has reduced? And because of that, we are taking radius as what? Half of the internucleus, half of the internuclear distance only. Na? So here there is no overlapping, so internuclear distance is going to be more. So we are taking half of that. So metallic radius is going to be more than that of a covalent radius. I hope this is clear to all of you. So please make a note of it. Yes, I hope we are done. Okay. Now let us go for learning the factors affecting atomic radius. So first one is Z. Z is nothing but atomic number. So if what does this atomic number tells you? It tells you about the number of protons, and protons are positively charged. So basically, if the number of protons increases, then definitely we expect that the force of attraction is going to increase, and if force of attraction increases, then what happens to the size? It is going to reduce. Okay. So we say if Z increases, that means the number of protons, they are increasing, and because of that, force of attraction, that increases, and due to that I am saying that the size is going to reduce. Okay. Another one is Z effective. This is effective nuclear charge, right? That means again it is telling you just about the nuclear force of attraction only. So consider it like that, nuclear force of attraction. Okay. So if Z effective increases, what is going to happen? Nuclear force of attraction increases on whom? The outermost electron. And because of that, we say that the size is going to decrease. Okay. So here I am able to say Z effective increases, and because of that, what is going to happen? Size is going to decrease. Third one is N, which is the number of shell. So if at all N increases, what happens to the size? Definitely size is also going to increase, because number of shells increases, automatically size increases. Fourth one, which is sigma, right? Sigma takes care of the inner electrons or else inter-electronic repulsions there. So if sigma increases, so the size increases, right? So sigma is taking care of the inter-electronic repulsions, okay? Inter-electronic repulsions. As such, out of all these four factors, majority of these two are, kind of you can easily remember, and they will be only of maximum use, okay? So make sure you are writing them. Then we are going to write down the general trend over there. Yes, are we done writing? Okay. Now let us proceed further, which is general trends of atomic radius in periodic table. So in a period when we are moving from left to right, so basically it is the Z effective which dominates, and because of that, what is going to happen? Size is going to reduce. In a group, when we are moving from top to bottom, so basically number of shell, that effect dominates. So we can say top to bottom, as number of shell increases, we say that the size will increase. T stands for here top, and here it stands for bottom, right? And I hope that is kind of, you can easily relate to left to right. So this I have given you a general trend, okay? But there could be some kind of twists and turns when it comes to different blocks here, and we'll see that first, okay? So first you make a note of it, then we'll proceed further. Yes, done writing? Okay, good. Now let us see trends of atomic radius in S, P, D and F block. Right. So all the generic as well as any exception if they are present in a particular block, it will be covered here itself. Okay. Now the first one is for S block. So in S block, if at all I see group wise, group 1, lithium, sodium, potassium, rubidium, cesium, right? We are not considering any radioactive elements here, right? So what is the general trend? It is following the general trend. That means as I move from top to bottom, size will increase since number of shell is increasing. The same holds true for the group 2, which is beryllium, magnesium, calcium, strontium and barium. So here also when you move down the group, size increases since N increases, right? Now let us see period wise also. That means across the period where these S block elements are present. So second period thoroughly we are taking. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? In this case, what is happening basically, suppose I am including neon also. So ideally what should happen, as I move from left to right, Z effective increases and because of that, size should reduce, right? So we can think of like this, size reduces, right? But for inert gases, by default, what we always take is the van der Waals radius. So due to van der Waals radius. So in general, we can say inert gases, they will have the highest size in their periodic table. If this is not there, so definitely this is like normal trend which is getting followed. Okay. Now, so third period, if at all I am talking about, third period, sodium, magnesium, aluminium, right? Silicon, phosphorus, sulfur, chlorine, argon. Here also the same thing, it keeps on decreasing up to chlorine and again if at all argon is there, so it will be maximum in size and again the reason will be van der Waals radius. So we can say in general inert gas will have maximum size in their corresponding period. In general I am writing, okay? So please write this down and we are done with the S block as such, right? Across the group as such and across the period also we have seen. So by default for inert gases we are considering the van der Waals radius. That is the reason we are having this here. I hope people are finished writing this. Okay. Now let us go for second one, which is P block, right? In P block, if at all I talk about group 13, right? So you're having boron, aluminium, gallium, indium, thallium. Normally, what do we expect? That as such size should increase as we are moving down the group, right? But the thing is, there is a kind of, a kind of deviation which happens here between aluminium and gallium, right? So basically, the correct order, if at all it is, so boron, gallium, aluminium, indium, and thallium. You are having something like this, right? And this I'll say that this is due to poor shielding effect, of d subshell electrons, right? So let us try to understand what I've written here. The thing is, when it comes to gallium, right? Gallium is 31, and before that, you just had first transition series, which is 3D series, right? Zinc you are having before it, 30, okay? Where 3D10 is there. Now, when I write its configuration, it will be argon 4s2, 3D10, 4p1, right? Now, if at all I arrange it shell wise, it will be like argon 3D10, 4s2, 4p1, right? So now if at all we try to understand here, suppose this is the nucleus and I'm just showing two shells here, which is third shell, and I'm showing this as the fourth shell, right? In that you are having two subshell S2 and P1, and here you are having D10, right? Now let us say because of this extra D10 electrons, you are having 10 protons also now here, right? Now the nuclear force of attraction will increase because of that extra 10 electrons which got added up in D. Why I am saying extra 10 electrons? Because when it was aluminium, it doesn't have any D orbital there, right? You'll be writing 1s2, 2s2, 2p6, 3s2, 3p1. You don't have any D there. So with like on comparing it with aluminium, I'm saying there is extra D, 10 electrons here, right? Otherwise, valence shell electron is having the same number of electrons in the valence shell of gallium as well as aluminium. So that's the reason I've written extra 10 electrons here. So because of that, extra 10 protons in the nucleus, because the as such atom is neutral, right? So what is going to happen? This nuclear force of attraction will first reach the third shell. In that third shell, it will encounter that 3D. Now 3D, we have already seen that D subshell doesn't have a proper shielding effect. Best is for S and then for P and then for D. So D doesn't have proper shielding effect. So will it be able to kind of stop this nuclear force of attraction? No. That means what? This will be sent to the outermost shell. So the outermost shell electrons start feeling more force of attraction, more nuclear force of attraction, and because of that, size reduces. So that's what we write due to poor shielding effect of d subshell electrons. So we also call it as d orbital contraction, or else we call it as transition contraction. Transition contraction means because of the transition series which has come up in front of that particular element, there is this kind of problem. Now the thing is, as we move away, that means as we proceed further from like group 13, that means as we enter from group 14 to 18, that effect is not seen much, okay? So the thing is, that's the reason we are going to write there is no exception in atomic radius from group 14 to 18. It's normal trend. So all of you first write this down and then we'll proceed further. Yes, people have written, we know. Okay. Now let us go further with the third one, that is in D block. In D block, let us see for 3D series. So in this we are having scandium, titanium, vanadium, chromium, Mn, iron, cobalt, nickel, copper and zinc, right? Now it is seen that it decreases up to manganese, then it almost become same for this, and for copper and zinc it will be increasing, right? Now the thing is here, basically I am saying that the Z effective is greater than the shielding effect. Shielding effect, that means we are talking about the interelectronic repulsion. Z effective, that means it is telling you about the nuclear force of attraction, right? So if Z effective dominates, then the size is definitely going to decrease. Here, that Z effective is almost same as the shielding effect. And because of that, size almost remains constant. And here what happens is, Z effective is basically, here shielding effect dominates. Shielding effect dominates. And because of that, we say that the size increases. Now you try to simply take this as, when I'm moving from scandium to Mn, there is like progressively the d orbitals or the d subshell is getting filled from d1 to d5, right? So at that time, the interelectronic repulsions are not that much, okay? So what is more dominating there? It is basically Z minus sigma I'm talking about. So Z, right? Z is increasing by 1. So because of that, overall Z effective is more, right? So if Z effective is more, definitely what is going to happen? More nuclear force of attraction and you are going to have size reduced. Now from iron, what happens is D6, that means the pairing of electrons starts. Okay. So here even the force of attraction increases, and at the same time you are having that interelectronic repulsions, they also start to increase. And when they start to increase, we say that the shielding effect, these two opposing factors, that means the force of attraction and the force of repulsion, they are trying to counterbalance each other. And we say that because of that, the size is almost going to remain constant. After that, suddenly in copper and zinc, we are writing what? D10, right? D10, that means the interelectronic repulsion is going to be high, right? So if it is going to be high, that is the reason we said that the shielding effect, which is basically your interelectronic repulsion, that is going to increase. And because of that, size is going to increase. So here you understand Z effective, that is nothing but the nuclear force of attraction. So nuclear force of attraction was dominating as compared to the as compared to the interelectronic repulsion. Then slowly, both of them, they almost kind of balanced each other. And then repulsion dominated, right? Clear about this? So make sure that you are writing it. So similar kind of trend is also there in the 4D and 5D transition series. So I'm just writing it only for the 3D series, right? That would be dealt in detail in D and F block elements, right? Here one more thing which we know is radius of 3D, radius of 4D and radius of 5D. That means if at all I'm talking about in a group, so this is what is seen, right? So basically this is due to poor shielding effect of F subshell electrons, right? In fact, we also say this is due to lanthanoid contraction. We'll understand this, don't worry about it. So let me give you example here. We have learnt now T zara half, right? Very noble Tata. Chromium most wanted, right? So basically this is forming 3D, 4D and 5D, right? In fact, I'll write little bit more closer here. 3D, this is 4D, this is 5D. When I talk about 3D, that means I am in 4th period. When I talk about 4D, I am in 5th period. When I am in 5D, I am in 6th period, right? Now it is seen that basically the atomic radius of these species, that means molybdenum is almost same as tungsten, zirconium same as hafnium, niobium, that means they're like nearby, almost equal to each other, right? So if somebody asks about titanium, zirconium, hafnium, the correct order of atomic radii should be this, right? So basically when we are having 6th period, right? So when we are having 6th period, so you already know in the 6th period, after filling of the 6s1, 6s2, you are having basically lanthanum. And after that, you are having cerium to lutetium, right? So cerium to lutetium, what you will be having is 4f electrons are getting filled up. So after lutetium only you are having this hafnium, this particular element which is having basically 72, right? Now the thing is hafnium you are having. So what will happen is, suppose if at all I talk about 6th period and here I am talking about 4th, 5th and 6th, right? So you are having 14 electrons in that F, you are having in D 10, like whatever is like the electrons here. Okay, some electrons in D here and some electrons in S and P, let us say, right? Now what will happen, because of, first of all, the nuclear force of attraction is going to go for this particular 4f subshell. The 4f subshell is going to have less shielding power, and because of that this is going to go for D, and there also less shielding power, and then it is going to go for S and P. So collectively what will happen, because of the very poor shielding effect of 4f here, that means F subshell electrons, the nuclear force of attraction has easily reached out to the valence shell electron, and hence there is a reduction in size. As such, we should think that accordingly as we are moving down the group, as the number of shell is increasing, so the size should have increased, but that does not happen, right? Because of the poor shielding effect. Okay, clear about this, everyone? Zirconium, hafnium, niobium, tantalum, molybdenum and tungsten. Scandium, yttrium and lanthanum. This is group 3. What about their size? They are going to have simple size increases since n increases. Here basically after lanthanum only you will be having 4f subshell getting filled up. So no effect on lanthanum. Getting it? Similarly, actinium also no effect on this, because after this only 5f subshell are getting filled up, right? Getting it? So it should be like normal trend for it. I hope this point is clear. Radius of 3D. For 3D, 4D, 5D, definitely 3D is going to be lesser than the 5D because of the shell number, right? But for 4D and 5D, ideally it should have been increased, but because of this lanthanoid contraction is nothing but when we move across left, like across the lanthanoids which are given to us, then there is a decrease in their size. And that decrease in the size is because of the poor shielding effect of F subshell electron, and that's what is lanthanoid contraction. Write this and then we'll proceed further. Are we done writing? So these are the trends for D block, and now let us move on for F block. So in case of F block elements, I am having lanthanoids. And when I talk about lanthanoids, I talk about cerium to lutetium, which is 58 to 71, right? Now in this case, we say that Z effective increases, and because of that, size decreases, right? So basically here what is happening is you are having Z effective as what? Z minus sigma, right? And if you remember in F block elements, what we say, in F block elements, we declare them as F block because the electrons are getting progressively filled in n minus 2f, right? So basically, this is also increasing by 1, this is also increasing, right? But the thing is, this sigma, it is not increasing to that much extent in comparison to this Z. So that is the reason overall effect will be Z effective increases, okay? So because of the poor shielding effect of your F subshell, you are able to see this, okay? Now, what about actinoids? In case of actinoids, we'll be having thorium to lawrencium. So basically it is 90 to 103. Here also we say that Z effective increases and the size is going to decrease. Okay. So now here I am writing in lanthanoids, as we move from left to right, there is a gradual decrease in the size, in their size. This is due to poor shielding effect, poor shielding effect of 4f subshell electrons. This phenomena is known as lanthanoid contraction. Is known as lanthanoid contraction. Similarly, in case of actinoids, it is the 5f subshell electrons which are causing poor shielding effect, and that is the reason we can call this as actinoid contraction. Okay. So in actinoids, as we move from left to right, their size decreases due to poor shielding effect of 5f subshell electrons. This phenomenon is known as actinoid contraction. So make sure you are writing this first of all. There I have written cerium to lutetium. Yes, I hope we have written this, right? So as such, we are done with the two of the atomic properties. One is Z effective, another one is atomic radius, right? So we'll stop here only for today. So you better revise all these concepts, okay? And definitely when I meet you next time, definitely we are going to do some questions, right? So at that time, basically, don't try to see your notebook. You must learn what has been taught to you and then apply those concepts. That way it will be much more beneficial for you, right? So I hope you enjoyed the session and you have learned a lot. So on that note, so I'm signing off and wish you all a very happy Vinayak Chaturthi in advance. Okay. So thank you and enjoy this festival. Thank you and have a nice day.